July 29th, 2025. It begins with a single region outlined in red, then within seconds the entire Pacific Rim flickers with tsunami alerts. What could trigger an ocean-wide cascade of warnings demanding millions to evacuate from Russia to Chile? At 23 hours, 24 minutes and 52 seconds UTC, something beneath the Kamchatka seafloor changed everything. But the first official alerts underestimated the true danger. How does one rupture ignite global alarm, and who decides when to run? At precisely 23:24:52 UTC on July 29th, 2025, a rupture tore through the Earth's crust beneath the Pacific, just off the coast of Russia's Kamchatka Peninsula. The earthquake's origin lay 35 kilometers below the seafloor, along the Kurilsk-Kamchatka subduction zone, a boundary where the Pacific plate grinds northwestward beneath the Okhotsk microplate at nearly 8 centimeters per year. For decades, stress had been building along a 390 by 140 kilometer stretch of this Megathrust fault. In that instant, the locked plates broke free. The overlying plate lurched upward, shoving the seafloor and the entire column of ocean above it several meters higher in a matter of seconds. This vertical displacement is what makes subduction zone quakes so dangerous. Unlike faults that slide sideways, a megathrust's upward snap launches a massive pulse of water, setting off tsunami waves that can race across the ocean at jetliner speeds. The sudden uplift, sometimes called the seafloor shove, is the spark that ignites a basin-wide alarm. The larger the area that moves, the more water is displaced and the greater the risk to distant shores. The 2025 Kamchatka rupture spanned nearly 400 kilometers, with sections of the fault slipping as much as 14 to 16 meters. This movement was not just a local event, it was a rearrangement of the seafloor on a scale matched only by the world's most powerful earthquakes. In the moments that followed, seismic waves rippled outward, and the first tremors reached distant monitoring stations. But in those first seconds, only the raw physics of the rupture mattered. An immense upward heave of the ocean bottom, invisible from the surface but enough to set the Pacific Rim on high alert. At 23:35 UTC, the Pacific Tsunami Warning Center pushed its first official message into the network. The bulletin, stamped with urgency, carried a magnitude estimate of 8.0, a formidable number but not yet the full story. Behind the scenes, analysts watched seismic traces roll in from stations scattered across the Pacific Rim. Their algorithms, tuned for speed, worked with the first arrivals, the sharpest, fastest signals from the nearest sensors, but the true scale of a megathrust rupture, especially one spanning nearly 400 kilometers, takes time to reveal itself. The initial calculation, based on short period waves, captured only a fraction of the energy released beneath the seafloor. As minutes ticked by, the center's duty officer fielded a barrage of data. Long period waves, which carry most of the earthquake's moment, moved more slowly through the Earth and arrived later. These signals told a different story. Each new dataset forced the system to re-evaluate. DART buoys in the Northwest Pacific, designed to detect subtle changes in deep ocean pressure, began transmitting their first readings. One buoy positioned just off the Kamchatka coast registered a 0.9 meter pulse, the second largest ever recorded by the DART network. Models updated in real time and the estimated magnitude jumped. Within an hour, the center revised its bulletin. The event was now classified as an 8.8, among the largest earthquakes of the century. For those tracking the alerts in real time, the rapid escalation sowed doubt. How could a quake grow so dramatically on paper in less than an hour? The answer lay in the physics of seismic waves and the limits of early algorithms. The initial underestimate was not a system failure, but a reflection of how much uncertainty shadows the first moments of a major offshore rupture. Each revision rippled outward, shaping evacuation orders and public trust across the Pacific. Every alert, every revision carried weight far beyond the numbers on a screen. Across the Pacific, millions watched their phones and televisions as the official bulletins shifted from an initial magnitude 8.0 to a far more severe 8.8. Each update forced people to recalculate should they stay put or run for higher ground. The uncertainty threaded through every decision. For some, the rapid escalation in warnings confirmed their worst fears and sent them moving, sometimes in the dead of night, sometimes with little more than the clothes on their backs. Others, seeing the magnitude jump so quickly, began to question the reliability of the system itself. If the experts could revise the threat in minutes, could the next message be trusted? This tug of war between trust and doubt shaped the response. In places where compliance was high, evacuation routes clogged and shelters filled, but not without cost. Injuries mounted, not from the waves, but from the scramble to escape. Falls on crowded stairways, car accidents in panicked traffic, and medical emergencies triggered by stress or exertion. In Japan alone, one person lost their life and 21 others were hurt during the rush to evacuate, all before the tsunami even arrived. The risk of injury during hurried evacuations is a hidden danger, one that grows when people must act on shifting, sometimes contradictory information. Communication became as vital as the science itself. The chain of trust linking warning centres to the public was tested with each revision, reminding everyone that the effectiveness of a warning is measured not just by how fast it is issued, but by how well it is understood and believed. Across the Pacific, the alert system snapped into motion. In Japan, sirens sounded up and down the coast. Local authorities ordered nearly 1.9 million people to leave their homes, filling evacuation centres and sending streams of headlights inland through the night. Harbour masters in Hokkaido and Tohoku radioed orders for vessels to head for deeper water, where tsunami waves lose their force. Cargo cranes froze in place as dock workers abandoned the piers. Coast Guard cutters patrolled port entrances, enforcing closures and warning off late arrivals. Thousands of kilometres away, the same urgency played out in Hawaii. The Pacific Tsunami Warning Centre's travel time maps projected arrival rings: 1 hour to Hokkaido, 8 hours to Honolulu, 10 hours to Chile. In Honolulu, advisory sirens blared and civil defence officials cleared beaches and harbours. Boat owners scrambled to cast off, hoping to reach safe depths before the first surge. On the US West Coast, port authorities in Crescent City and Monterey halted operations, and police cordoned off waterfronts. In French Polynesia, Chile and Ecuador, emergency bulletins flashed on TV and mobile phones, instructing residents to stay off beaches and away from river mouths. The Pacific Tsunami Warning and Mitigation System, a network of sensors, satellites and emergency protocols, linked these distant regions. Each decision, whether to evacuate, clear a harbour or issue a warning, was shaped by real-time data and the evolving forecast. The result was a basin-wide mobilization, millions moving, ports emptying, and a continent-spanning chain of readiness, all triggered by a single rupture far beneath the sea. Severo-Kurilsk stands exposed on the Kuril Islands, where deep ocean trenches send Pacific waves straight to its shore. When the tsunami struck, the water did not come as a single surge, but in a series of waves, each one building on the last. Local officials remember the shock as the second wave rose higher than anyone thought possible, flooding streets and tossing boats onto rooftops. Tide gauge records confirmed the largest surge arrived in that second pulse, a pattern seen in many tsunamis. Just south in a narrow river valley near Vestnik Bay, the disaster took on a different scale. Survey teams measured a run-up of 33.1 metres over 100 feet. It was one of the highest ever recorded. Here, the steep, confined inlet acted as a natural amplifier. The tsunami's rhythm matched the bay's own resonance, stacking each wave until water climbed far above normal levels. Elsewhere, the coast saw only minor swells. Bathymetry alone shaped these extremes. Danger did not fade with the retreat of the first wave. Deep ocean sensors known as dart buoys continued to record sharp oscillations long after the initial surge. One buoy just off Kamchatka captured a second wave spike nearly as large as the first, evidence that tsunami energy was still moving through the basin. In Severo-Kurilsk and other harbours, currents ran fast and unpredictable, dragging debris and making rescue work hazardous for hours. Tide gauges traced a restless pattern. Water levels rose and fell in cycles, refusing to settle back to normal. The all clear could not be declared on a single schedule. Persistent waves and surges meant authorities kept ports and beaches closed well into the next day. The earthquake's violence did not end with the tsunami. Over the following weeks, the United States Geological Survey catalogued 3,517 aftershocks, including 27 above magnitude 6.0. Each new tremor forced emergency managers to weigh the risk of fresh evacuation orders, especially when larger aftershocks struck offshore. Across the Kamchatka Peninsula, landslides, 346 in total, cut roads, damaged infrastructure, and left entire communities isolated. Then, as recovery efforts stretched thin, Kliuchevskoye volcano began to erupt. Ash plumes and glowing lava lit the sky, a reminder that in the ring of fire, hazards rarely travel alone. While scientists cautioned against drawing a straight line from quake to eruption, the timing underscored the region's volatile nature. For those living along the Pacific Rim, the lesson was clear. The threat is not over when the first warning fades. True safety comes only when the long tail of hazard, waves, aftershocks, and even volcanic unrest finally recedes. Pacific warning maps can light up in minutes, but real certainty lags behind. Each alarm tests not just technology but trust, because even a small tsunami can upend lives on distant shores. Coastal risk will not wait. In this era of rapid alerts, readiness remains the only constant.